Bismillah ar-Rahman ar-Rahim. Now, after we discuss the meaning of convergence of sequences, we will move to a very important topic. It's called infinite series. So what is an infinite series? This is what we have here. So we start with the notation first, some notations to distinguish between sequences and series to see the difference. Then we will discuss what is the meaning of convergent series. Okay, we know what is the meaning of convergent sequence. What is a sequence actually? A sequence is just a list of numbers written in definite order. So it is A1, A2, A3. It's like readings. We have the first reading, the second reading, third reading, etc. This is what we discussed before. Now we move to another notation which is called series or infinite series actually. What is an infinite series? Is the sum of these elements. So it is A1 plus A2 plus A3 where these elements is moving here indefinitely. We have infinite readings, let us say, and we are interested to see is this series convergent or not convergent. So what is the meaning of convergent series? We know what is the meaning of convergent sequence. We said if the limit of the nth term is finite as a real number, we say it is a convergent sequence. But what does it mean, convergent series? That will be our first definition here. It says, okay, you are investigating the meaning of convergence of such a notation here, which is called infinite series. The definition is as follows. You start with a series, which is an infinite series. Then we will move back to the sequences. How to move back to the sequences? We will define what we call the sequence of partial sums. What does it mean? Okay, we have here up to infinity, from n equal to 1 up to infinity. So we are moving indefinitely. So what we will do here, the usual trick we do in mathematics, we remove infinity and we will investigate what's happening if we move from 1 to n. Then we need to push that n to goes to what? To infinity. So we will define this sequence of partial sum as follows. So what is Sn? It says, okay, let Sn denotes its nth partial sum. What do you mean by nth partial sum? Sn is equal to the summation of the first n elements. So for example here, if I say this is what is the series given here, this is what we have here. An n equal to 1 up to infinity. Just to understand the meaning of this Sn equal to what? You see we have here A1 plus A2 plus A3 plus A4 plus blah 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 plus An plus 1, and this will move up to infinity. It's going. We will define this new sequence now. We will move from a series to a sequence. How? We define the first element in that sequence to be the first partial sum. Partial sum, it means part of the whole sum. So what we will do here, we take only the first element. We call it the first partial sum. When we go to S2, the second partial sum, what does it mean, second partial sum? We will take the sum of the first two elements only. So it is A1 plus A2. We will stop here. That's called the second partial sum. Similarly, you have the third partial sum is the summation of the first three elements and so on. This is up to here. All the way, we are getting these points and throw them in a set. This is S1, this is the second one, S2, this is S3, and so on. What is Sn? What is the nth partial sum as defined there in the definition? Sn is the sum of the first n elements in the series. So we will take A1 plus A2 plus A3 and so on, A3, until we reach the last element is An. We call this one the nth partial sum. So it is a real number at the end. We are adding finite number of readings. Again, we will throw it here in the sequence. We will construct now a sequence of numbers. This sequence is called the sequence of partial sums. Why? Because its elements, just the elements of the partial sums. We are getting partial sums here. I throw them in the sequence. So we call the sequence is the sequence of partial sum. Now, let's move and read the rest of the definition. So, okay, we constructed the sequence of partial sums whose elements are the partial sums of the whole sum we have here. The definition says if this sequence, which is the sequence of partial sum, is convergent, and we know what is the meaning of this because we discussed the meaning of convergent sequences. And if we say it is convergent, it means the limit as n goes to infinity of Sn is equal to a real number. Finite real number exists as a real number. That's what it means, convergent sequence. Then we will say that this series itself is convergent. Not only convergent. It's convergent with the sum equal to S. The total sum will be exactly equal to S. Now, if the sequence of the partial sum is divergent, we say simply what? The series is divergent. Just to clarify it more, this is what we start with. This is our infinite series, n equal to 1 up to infinity. And this is an, and this is what we are trying to see if it is convergent or not. What we did here, we start moving infinity out. So we put here n, another index to be moving now, and this is ai. We will find this sum, which is finite at the end, which is written in terms of n. Then we are discussing the limit as n goes to infinity of this. So we are moving infinity, we are inserting, and then we discuss the issue here, and then we push n to goes to infinity. So if this final thing here will be finite, then we say this is convergent, and the sum is equal to the limit of this. Assuming this is equal to S, then we say this series is convergent, and the value of it is equal to S. The sum of it is equal to S. Otherwise, we say the series is divergent. Okay, that is what's the meaning of convergent series. Now we will apply this definition in some specific type of series to see whether they are convergent or not convergent. We will say if it is not convergent, we usually say it is divergent, as the definition says here. If the series is not convergent, then it's called divergent. We will start by testing the geometric series. What does it mean, a geometric series? And telescoping series. Then also we will study the importance of the nth term in the series, an. And we will talk about one test says the nth term test of divergence. That will be done in the following parts. Now let us apply this definition in the given example here. The example says find the sum of the series. We are given a series that has the form a plus ar squared plus ar n minus 1, that's the nth term, plus ar to the n, and etc. Here we assume that a is not equal to 0. Otherwise, we have the 0 series here, and the 0 series, we can discuss it separately. Okay, let us assume now a is not equal to 0, so we have this kind of series. What is the definition? What is the meaning of convergence of series? We need to apply the definition. The definition says if we need to start explaining the meaning of convergence, we need to move back to the sequences. How to move back to the sequences? We define what we call the sequence of partial sums. Let us define this sequence of partial sums. So what is the nth term in that sequence, Sn, that we need to take the limit as n goes to infinity? It is the summation of the first n elements. The summation of the first n elements is given by a plus ar squared plus etc. until we reach the nth element, that is ar to the n minus 1. That's what we have exactly for Sn. Now, our challenge is this. What is the limit? What is the limit as n goes to infinity of this Sn? Is it finite? Is it a real number? If it is a real number, then we say the series is convergent, and the sum is equal to the sum of that. If it is not, then what will happen here? So, how to find the limit actually for Sn, and we have sum of n elements here. It's not straightforward, but for this specific series, I'm talking about the limit as n goes to infinity of the sum. In order to find the limit as n goes to infinity, we need to simplify this. We need to have a formula for Sn. We need to simplify the form of the nth partial sum. Then we can push n to goes to infinity. So what we will do here, specifically for this exercise, we have a nice trick to simplify the expression of Sn. So what is that? We will multiply by r. Okay, r times Sn. What is it equal to? And then I will say why we multiplied by r here, because you can see this is a, this is ar. If you divide the second element by the first element, that is ar divided by a, that will give you always r. If you just divide the third by the second one, ar squared divided by ar, then again this is equal to r, and etc. This is equal to the next by divide, and so on. This is always the ratio between two elements in the series. The ratio is always fixed number, which is equal to r. So that's why if we multiply by r, we will get similar expression. We get this, AR plus what? If you multiply by r, this will be AR squared. Plus here we have AR cubed plus what? This is AR to the, there is an element here, which is AR to the n minus 2. When I multiply by r, it will be a times r to the power n minus 1. Plus, this will be AR to the power n. Okay? This is r squared, this is r to the power 1, this is r to the n minus 1. The previous one is r to the n minus 2. So once we multiply by r, we get AR to the n minus 1. Okay, fine. What I will do here, I will try to subtract them. Sn minus this. So this implies, look carefully for this expression, Sn minus r times Sn. What do we have? If we say Sn minus this, so I multiply everywhere here by minus sign, minus sign, minus sign. So what will happen in that case? You will see that AR will be cancelled with AR. AR squared will be cancelled with AR squared. There's an AR cubed here will be cancelled with AR cubed. We have AR to the n minus 1. It will be cancelled with AR to the power n minus 1. What are the two terms will survive at the end is this, the element A, and last one is the element AR to the power n only. All other terms will be deleted. This is interesting now. Can we find an expression for Sn? Yes, if we take Sn common factor and divide by the 1 minus r, that's what we have at the end. We have Sn is equal to, it will be what? It will be A minus AR to the n divided by what? Divided by 1 minus r. How to get this 1 minus r? Actually, just we take here what? We take Sn common factor. Then I will have 1 minus r is equal to A minus AR to the n. And simply I divide by 1 minus r. Now the question is, this is the nth term. Is this sequence of partial sum convergent or not? When it is convergent, when it is not convergent. We need to discuss the limit of Sn as n goes to infinity. So you can see now here that the limit of Sn as n goes to infinity will exist only if what? Look here. Look carefully for the expression we have. A minus AR to the n all over 1 minus r. Okay. First, we need r not to be equal to 1. If we have r equal to 1, we have problem here. We are dividing by 0. So this will not be convergent. That's one thing. The second one, okay, if r is not equal to 1, now this is a finite number. This is a real number at the end. Okay, this is a real number. We assume from the beginning A is a real number, so we have no problem here. What it remains is this, r to the n. And we know from our previous discussion that the limit as n goes to infinity of r to the n, this one exists only if this is equal to, if you remember, we discussed this one before, it says the limit as n goes to infinity of Rn will be equal to, of course, if r equal to 1, this is equal to 1 if r exactly equal to 1. And it's equal to 0 if absolute value of r is less than 1. Otherwise, it is divergent. If r greater than 1 or less than minus 1, then this sequence is divergent. So we have convergence only between minus 1 and 1 for r to the n. It is divergent here for the r is less than minus 1, and it is divergent for r greater than 1. Okay, but again we have problem at r equal to 1. So what is the conclusion then? The conclusion then is this. This will be equal to A over 1 minus r. Why? Because if absolute value of r is less than 1, strictly less than 1, then this will go to 0. And we have A over 1 minus r. So that is convergent. This is equal to this if we have what? Absolute value of r is less than 1. Why less than 1? Not less than or equal to. Less than 1 because this is convergent for, yes, it is between minus 1 and 1 closed, but we need the r not equal to 1 because we are dividing by 0 otherwise here. So in that case, we have the limit of Sn equal to a over 1 minus r only if absolute value of r less than 1, and the limit of Sn as in goes to infinity does not exist if absolute value of r is greater than or equal to 1. So what is the conclusion then? The sequence of partial sum is convergent only if absolute value of r less than 1. Not only that, and the value is a over 1 minus r. Meaning the series, this specific series is convergent only if absolute value of r less than 1. Not only convergent, the sum of it is a over 1 minus r. That's one thing. The second one, if absolute value of r greater than 1 or equal to 1, then the sequence of partial sum is divergent. So the series is divergent. Now let us summarize. First, the name of this series is called the geometric series. It's called the geometric series. And this discussion we made here, it's called geometric series test. Meaning, if you have a question about a series that has the following form or this specific form, then this is called geometric series. So what is the property of geometric series? The division of two terms in sequence will give always the same ratio, real number r. That's one thing. Second one, the test says if absolute value of r less than 1, it's convergent, and this is its sum. If absolute value of r greater than or equal to 1, it is divergent. That is what we call geometric series test, and this is how to apply the definition of convergence and divergence sequence, or the meaning of convergent sequences. Okay, now let us summarize what we did. We have here the geometric series. As we said, this is called the geometric series. The geometric series, which is given by this, ar to the n minus 1, that's the standard form here, a plus ar square, etc. Then this series is convergent if absolute value of r less than 1, and not only this, has the sum exactly equal to a over 1 minus r. If the absolute value of r greater than or equal to 1, the series is divergent. Let us see now how to apply this in some examples. For example, here the first one says find the sum of the series 5 minus 10 over 3 plus 20 over 9 minus 40 over 20 plus. Okay. Is this series convergent, not convergent? If it is convergent, what is the sum? What type of series we have? We need to investigate. Okay, is it geometric series? How to test if it is geometric series or not? The only thing we need to do, we need to check if it is geometric series. So I will check this first. Check if it is geometric series. What I need to do, I take the two terms and divide. So for example, I will check minus 10 over 3, the second term, divided by 5. What is it equal to? This is equal to minus 10 over 3 multiplied by, this is 5 over 1. So this is equal to 1 over 5. That is simply equal to, if you simplify it here, you get minus 2 over 3. Okay, fine. What about the third term by the second term? Okay, I have 20 over 9 divided by minus 10 over 3. So it is multiplication of minus 3 over 10. If you simplify, this will give you what? Over 3 over 3, this will be 3 over 10 over 10, this will be 2. So it is again minus 2 over 3. And you can see more if you divide the fourth by the third one. Again, you have minus 2 over 3. So the conclusion that the division of two terms in sequence of the series always gives the same number, the same ratio. So it is a geometric series indeed. If it is a geometric series, is it convergent or not convergent? So by this observation, we say this series is geometric. So if it is geometric series, what is the conclusion now by the test we have here? We need to observe two things here. What is A? A is the first element, so it is 5. And what is R? This is most important actually. We have absolute value of R. We say since now absolute value of R is equal to absolute value of minus 2 over 3, which is actually 2 over 3. That is less than 1. So what is the conclusion? This is less than 1, so the series is convergent. So the geometric series is convergent. Not only convergent, it is convergent, not only convergent. It has also a sum form in that case. If we have a convergent geometric series, that is one of the most beautiful series we have, where we can find the exact sum. Not only we know it is convergent, we know what is the exact sum. What is the sum with? Sum is equal to, according to the formula we derived, it is A over 1 minus R, and that is equal to, what is our A? Our A is the first element in the series, that is 5. So A is equal to 5, fine. Okay, this is 1 minus, what is R? R is minus 2 over 3. So this is equal to 5 over 1 plus 2 over 3, that is actually equal to, if we multiply by 3, this will be 15. The numerator, this will be 3 plus 2, that is 5. So the total sum will be exactly equal to what? Equal to 3. So if we add these infinite numbers, 5 minus 2 over 3 plus 20 over 9 minus 40 over 20, etc. At the end of the day, we will have the answer equal to what? Equal to 3. This is according to the definition of what? Convergent of series. We will see another example about geometric series. More examples about geometric series now. Okay, more examples about geometric series. We have a series here says test, or the question says test the series for convergence. So is it convergent or divergent? Why? Okay, we have two options here to move. Let us look at this in two different angles. Either we just rewrite it in the standard form to decide, so it is n equal to 1 up to infinity. The standard form is like this. You need to separate A, and then you have R to the n minus 1. That is the standard form of a geometric series. This is one option. So let us try to do that. We have the series given to be n equal to 1 up to infinity, and that is 2 to the power 2n. And we have here 3 to the power 1 minus n. I'm trying to rewrite it in standard form. So what I will do here, I will just rewrite it this way. N equal to 1 up to infinity. I will take this as 2 to the power 2 to the power n. So it is 2 to the power 2 all to the power n. That's one thing. Times. I will write this one as 3 to the power minus n times 3 to the power 1. I'm just using the properties of exponents. Okay, fine. So what is this equal to? This is equal to summation of n equal to 1 up to infinity. And that is 4 to the n over 3. So that is 4 over 3 all to the power n. Okay, I can take this one down in the denominator with the 3 to the n, and this is 4 to the n. So it is 4 over 3 to the power n multiplied by 3. Not yet, because I need this one to be to the power n minus 1. So what I will do here, I will separate 4 over 3, so that will give me this, n equal to 1 up to infinity. I have 3 times, I will separate 4 over 3, so what it remains here is 4 over 3 to the power n minus 1. Then I simplify 3 with the 3 here. Now it is exactly in the standard form of a geometric series. You can read clearly the value of A is equal to 4, and the value of R is equal to 4 over 3. So I have A equal to 4, and R is equal to 4 over 3. Actually, this is the most significant part we need. Because once this is the absolute value of R is less than 1, the series is convergent. Whenever it is greater than or equal to 1, it is divergent. And clearly here, so we have absolute value of R is equal to 4 over 3. That's greater than 1. So the series is what? The series is divergent. This is a geometric series. So it is a divergent geometric series. The geometric series is divergent because we have absolute value of R is greater than 1. So I will say here specifically the geometric series is divergent because this is valid only if we have a geometric series, and it is a geometric series in this case. That is one option to figure out what is A, what is R. Another option to do that, if you like, you can do it alternatively like this. You can say this is equal to n equal to 1 up to infinity. Okay, we have 2 to the power 2n, and this is 3 to the power 1 minus n. Either you just rewrite it in standard form as we did before, or the only thing you need to do is just separate few terms and see whether it is geometric or not. Okay, if you just substitute 1, for example, here you have 2 to the power 2, that is 4, okay, and if you substitute 1 here, you get 1 minus 1, it is 0, 3 to the power 0 is 1, times 4, that is 4, plus. And the next one will be just substituting 1. You substitute 2 now, 2 times 2 is 4, 2 to the power 4 is 16, and if we substitute 2 here, 1 minus 2 is minus 1, so it is 16 over what? Over 3, okay? That is the second term. The third term, you substitute n equal to 2, etc. Okay? And then, the only thing you need to find A and R. This is A equal to 4. So, as we had before, A equal to 4. How to get the value of R? R is equal to 16 over 3 divided by 4. So, it is multiplied by 1 over 4. If you simplify here, okay, over 4. So, that will give you 4 over 3, which is the ratio we have here, 4 over 3. So, we can conclude that this is a geometric series and it is divergent. Of course, we need to find more terms if we need to check if it is geometric series or not, okay? So if the question says test the following geometric series for convergence, I need only to figure out what is A, what is R. From R, I can conclude if it is convergent or not. From A and R, I can get what? The sum of it if it is convergent. So in this exercise, it is divergent for the reasons we mentioned here. We have A equal to 4 and R is equal to 4 over 3. For the reason that R is greater than 1, it is divergent. Okay. What is our next example here? You know, when we define the rational numbers, we define rational numbers. Let me just recall this. We define rational numbers by saying that it is a number of the form P over Q, where we have P and Q, what? P and Q are integers. And we have Q not equal to 0. We have the denominator is not equal to 0. So we define rational numbers like this. Always we can rewrite it as P over Q, where P, Q are integers and Q is not equal to 0. But also we have an equivalent definition for this. We say a rational number, or the set of rational numbers, consists of all terminating, repeating decimals. Meaning, if I have a terminating decimal, like for example 0.23, this is a rational number. Why it's a rational number? Because easily you can see that it is written like 23 over 100, for example. Okay. If we have something like 0.6 repeated, is this one rational or irrational? The definition is no. It says it is irrational. Why? Because it is repeating decimals. It is 0.6666, etc. indefinitely. But is it clear how to rewrite this? Can we rewrite this one as P over Q? For the first one, yes. If it is terminating, always we can write it as a rational number of the form P over Q. The question now is this. If we have such type of numbers, can we rewrite them as P over Q? The answer, of course, yes. And this is one application for geometric series, will be explained in the following exercise. Okay, let us see now how to rewrite a rational number which is written in decimal notation as fraction of P over Q, as what we explained before. Okay, we have 0.6 repeated. 0.6 repeated. What does it mean, 0.6 repeated? It means it is 0.666, etc. Up to infinity. It will not stop. The same system will be repeated. It's the same digit is repeated here. Okay, fine. So we can look at this actually from another option here, another point of view. We can rewrite this one as sum of numbers. 6 over, this is the 10th digit here, 6 over 10, plus the second digit is 6 over 100, plus the third one is 6 over 1000, okay? And so it is 6 over 10,000, and this will continue like this, okay? We are rewriting the same number, but in summation stuff here. Look for this summation, which is an infinite series actually. It is not stopping here, okay? Look at it carefully. Just take care of the division of two numbers in sequence and see if it gives the same ratio all the time. Meaning, if I divide this number by this, the third one by the second one, the fourth one by the third one, and so on, will we get the same ratio here? Okay, clearly, if I divide 6 over 100, for example, if I divide this one by 6 over 10, it's like I multiplied by 10 over 6. So this is exactly equal to what? If you simplify, this will be 1 over 10. And you can see also, if you divide the third one by the second one, 6 over 1000 divided by 6 over 100, so it's multiplied by 100 over 6. This will give you also 1 over 10. And if you divide the fourth one by the third one, also it is equal to 1 over 10. So actually you can rewrite this if you like. I checked that it is geometric series. You can also rewrite this one as, you can rewrite it like what? You can rewrite it as, this is a sum of infinite sum from n equal to 1 up to infinity. Okay, this is 6 over 10 multiplied by 6 over 10 to the power, sorry, this is 6 over 10, and this is 1 over 10 all to the power n minus 1. Let us check this. If n equal to 1, this will be 0, so this is 1, so we have 6 over 10. If n equal to 2, this will be 2 minus 1, so it is 1. 1 over 10 times 6 over 10, that is 6 over 100. If n equal to 3, this is 1 over 10 to the power 2, so it is 1 over 100 times 6 over 10, so that is 6 over 1000. This is exactly what we have in geometric series form. This is exactly now written in the standard form of a geometric series. So it is a geometric series, so the sum is a geometric series with the following properties. We have A is equal to 6 over 10, and we have R is equal to 1 over 10. Okay, clearly now absolute value of R is 1 over 10, which is less than 1, so it is convergent. Not only convergent, we can find the sum. Okay. Now you clearly we have here now, since absolute value of R, which is equal to 1 over 10, is less than 1, it is what? It is convergent. And the beauty of this type of series, not only convergent, and the sum is equal to. The sum is equal to A over 1 minus R, and this is equal to what? 6 over 10, that's equal to A. So it is 6 over 10 divided by 1 minus R, that is 1 over 10. And that is equal to, if you multiply by 10, this will be 6, this will be what? This will be 10 minus 1, that's equal to 9, and this is exactly equal to, if you divide by 3, this is equal to 2 over 3. And we can check this one, that 2 over 3 is nothing but 0.6 repeated. Let us check that. That 2 over 3 is 0.6 repeated. This is point, okay? Then we have 20 here. 20 divided by 3 is 6. By 3, this is 18. The remaining is 2, so it's again 20. So it is 6 again. This is 18, and etc. You have 20. So this will be 6, and it will be repeated like this. So this is how to move from a number written in decimal notation, repeated, into what? Into a ratio of two numbers by using the help of what we call geometric series. Okay, more examples, because this is very important type of series. Let us take one more example about geometric series. Now, a very important example we will discuss now, which is important in the sense that we need later to represent a given function by power series. That will be our application part for the series job. Okay, what is that question? It says find the sum of this kind of summation. We have n equal to 0 up to infinity, x to the n if absolute value of x less than 1. Okay, if we look carefully for this expression here, we have n equal to 0 up to infinity. We can easily see that this is a geometric series. Why? Just open a few terms and you will see. If n equal to 0, this will be equal to 1. If n equal to 1, this is equal to x. Then x squared, then x cubed, and etc. Clearly, we have a geometric series. Why? Because once we divide x by 1, we have x. X squared by x, we get x. And x cubed by x squared, we get x. And so on. So we have the same ratio all the time. This is a geometric series. And he mentioned in the question that absolute value of r, absolute value of x, which is absolute value of r, actually is less than 1. So it is convergent geometric series. It is a geometric series with the following. Absolute value of R is equal to, in this case, R is equal to X, so it is absolute value of X. Okay, this is, now, since it is less than 1, so it is what? So it is convergent. It is convergent geometric series, and since it is convergent geometric series, the sum is exactly equal to what? The sum is equal to A over 1 minus R. Here we have A equal to what? We have A equal to 1. R is equal to X. This is what we have for the series. We have A equal to 1, R is equal to X. So we apply it here. We have the answer to be 1 over 1 minus X. What does it mean now for you? It means if you just go here and write this one as infinite series n equal to 0 up to infinity, that is X to the n, then this is exactly equal to 1 over 1 minus X. But this is not enough. Writing it this way is not enough. Writing it like n equal to 0 up to infinity, X to the n equal to 1 over 1 minus X doesn't make any sense unless we specify the domain, meaning the values of X for which this is convergence. So we always say that this is exactly equal to this if absolute value of X is less than 1. Otherwise, we may come or end up with some conclusion that doesn't make any sense. Let me specify this for you or make it clear for you. Why it is very important to specify that absolute value of X less than 1? First, because it is a geometric series and the geometric series convergent only if this is less than 1. So it's like we say that the domain of this is only between -1 and 1. Why this is very important? Maybe someone will come and say, okay, you said this is equal to this, so it means 1 over 1 minus X is equal to 1 plus X squared plus, blah, 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 like this. Okay. If we do not specify this, if we do not specify the domain of the series when it is convergent, maybe someone will come and say, okay, I will substitute X equal to 2. If we substitute X equal to 2 on both sides of the equation, what do we have? Here we get 1 over 1 minus 2, that is -1. And in the other side, here we have 1 plus 2 plus 4 plus. So what does it mean? It means you are adding infinite times positive numbers, and at the end of the day, you are getting what? You are getting a negative number. And does it make sense here? This is totally wrong. Why totally wrong? Because we are substituting a point which is not allowed. It is outside the domain of the series where we specified it to be between -1 and 1. But if you specify, for example, X to be 1/2, 1/3, 1/4, etc., -1/2, minus any number between -1 and 1, this is always true. So to make it precise, always you need to specify when it is called. Now it is complete statement. This is equal to this if absolute value of X is 1. Otherwise, it doesn't make any sense. This is what we mean by geometric series. Now we will discuss another type of series. It's called telescoping series, and we will see how to test for convergence. That will be our next point. Okay, before we go to this example, which is another type of series, let us say some words about the previous example we have here. That is the function f of x, 1 over 1 minus x equal to 1 plus x squared plus, etc. We said this is always true only if absolute value of x less than 1. That's the condition for geometric series. Now looking at this carefully, we have what here? In the left-hand side, we have a function, which is 1 over 1 minus x. In the right-hand side, we have a series. So in this case, we are representing this function by a series. But you need to be careful here because the domain of the function here is from -infinity to infinity, except at a point 1. But the domain of the series here is between only -1 and 1. So they both agree if absolute value of x less than 1. Not in the whole domain. It's in a restricted domain. This question, which is representing a function by a power series, does a function have a power series representation? And if it has a power series representation, how it can be found? This will be discussed later. Now, our challenge now just to discuss the convergence and divergence of series. We will do this for the following exercise. This is just a comment about the previous example. Now, let's come to this nice series we have here. Show that this series is convergent. So we know it is convergent, but How to find the sum if it is convergent? We need to show it is convergent, then we need to find the sum. Fine. Let us look at this series from another, again, angle. We have here n equal to 1 up to infinity. This is actually, all of this is called an, right? This is our an. So what I will do here, I will try to rewrite this an, 1 over n plus 1, in different form only. So what I will do here, I will use the previous discussion we made in integration by partial fraction to decompose this fraction into two fractions. So I will write it as something over n plus 1. As we did before, we said, okay, we substitute 0 here to have the constant for 1 over n, so that is 1. The constant over n, that's equal to 1. For the other one, I will cover this and substitute minus 1. I have minus 1 over n plus 1. So what I will do here, I just copy the same thing here, but in different form. I will write it as 1 over n minus 1 over n plus 1. Fine. This is what we are trying to investigate here. How to investigate for convergence? We go back always at the beginning here by definition. What is the definition? The definition says, first we need to construct Sn, the nth partial sum, then push n to go to infinity and see the result. If it is there, then it is convergent. If it is not there, then it is divergent. So let us do that. Let us form first Sn. What is the formula for Sn? What is the meaning of Sn? Sn is the sum of the first n elements in the series. So let us substitute by 1. So that will give me 1 minus 1/2. That is actually A1. All of this is just A1. This is A1 plus the second element, A2. Substituting 2, we have 1/2 minus 1/3. This is actually, all of this is just A2. And we need to move up to what? Up to the last element, or the one before the last element. I will substitute instead of n minus 1. Instead of n minus 1, so I get what? 1 over n minus 1, and that is minus 1 over n. This is actually the n minus 1 terms. This is an minus 1. The last one is an. An is 1 over n minus 1 over n plus 1. That's exactly what we have for Sn. This is the definition of Sn. Now, we will see if this Sn can be simplified somehow so that we can answer the question, what is the limit of it as n goes to infinity? And clearly you can see here, there is a nice cancellation behavior here. Look, minus 1/2 will cancel with 1/2. Then minus 1/3 will cancel with 1/3 here. 1 over n will cancel with the previous one here. 1 over n minus 1. Minus 1 over n and 1 over n cancelling each other. So it's like we are moving in a telescope. Okay? So what's going on here? This term will cancel with the next one. This term will cancel with the next one. This term will cancel with the previous one. This term will cancel with the next one, and so on. So what terms, or which terms will survive at the end? You can easily see that Sn here in this case will be equal to what? Only the first element and the last element, 1 over n plus 1. So we succeeded now to simplify the expression of Sn, and we get it only 2 terms. Now we answered the question, what is the limit as n goes to infinity of Sn? Clearly it is equal to the limit as n goes to infinity of 1 minus 1 over n plus 1, and that is exactly equal to what? Equal to 1. As n goes to infinity, this always goes to 1. Now this will give us 2 things. Since the limit of Sn equal to 1 exists as a real number, finite number, then the series given is convergent. Because the sequence is convergent, the sequence of partial sum is convergent, the series is also convergent. Not only this, the sum of the series exactly equal to the limit of the partial sum, which is equal to 1. So in this case, so by definition, the series is convergent. This is one thing. Not only convergent, and its sum is, which is the summation of summation n equal to 1, if you like, up to infinity, 1 over n plus 1. This will be exactly equal to the limit of the partial sum sequence, or the sequence of partial sum, which is equal to 1. So we say in this case, by definition, the sum of the series exactly equal to 1. This series is called telescoping series. This series is called telescoping series, and this is the way we can find the sum of the series. So this is called telescoping series. This series, the above series, the previous series. Let us say this series, or this type of series actually. Let me write it this way if you like. These of series are called telescoping series. Okay, so we give it a specific name here. It's called telescoping series. Fine. Let us see another example about telescoping series and see how to find, whether it is convergent, divergent. Is it always a telescoping series supposed to be like a rational function? This way we can use partial fraction. Not always. We have different types of series, and when we do the nth partial sum, we will see that the cancellation behavior is the same, okay? And then in that case, we call it telescoping series. So let us do another exercise about telescoping series and see if it is convergent or not convergent. Okay. We have this another example. Let's call it part B, if you like. And we will see if this is convergent or not convergent. We have a series coming this way, n equal to 1 up to infinity. It is tangent inverse of, let us say here, 2n minus 1 minus tangent inverse of 2n plus, this is 2n plus 1. This is what we have. This is exactly the nth term of the series. This is tangent inverse 2n minus 1 minus tangent inverse 2n plus 1. Fine. Test for convergence. Show it is convergent. Find the sum. We'll see how to deal with this. Okay, as what we did before, we have to find Sn. This is the definition. That's always the first step. We need to find Sn. That is the sum of the first n elements. So I substitute 1 here to get what? Tangent inverse of, what is that? 2 times 1 is 2 minus 1. That's tangent inverse of 1 minus tangent inverse of 3. That's the first element in the nth partial sum. Plus the second element in the nth partial sum, here we have n equal to 2. So this will give, it will give what? Tangent inverse of 3, okay, minus tangent inverse of 5, okay. Plus, let us add more terms. Okay, the next one, if n equal to 3, this will be tangent inverse of 5, minus tangent inverse of 7, okay. Fine. Okay, fine. Let's move to the last one. The last one is tangent inverse, which is the nth term. Actually, it is tangent inverse of 2n minus 1 minus tangent inverse of what? 2n plus 1. Fine. Again, if you look carefully for the nth term, it can be simplified. Look, tangent inverse of 3 minus tangent inverse of 3 will be cancelled out. Tangent inverse of 5 minus tangent inverse of 5 will be cancelled out. Tangent inverse minus tangent inverse of 7 will cancel with the next one. Tangent inverse of 2n minus 1 will cancel with the previous one. So you end up with what? You end up Sn is just equal to tangent inverse of 1 minus, in this case it is tangent inverse of 2n plus 1. Fine. Now, the question of answering convergence of series is reduced now to what? To answer the convergence of sequences. And we know what is the limit of this as n goes to infinity. As n goes to infinity of Sn, it is equal to, okay, the limit of this is just pi over 4 because this is constant at the end, tangent inverse of 1. As n goes to infinity, this is a tangent inverse continuous, so we can talk about the limit of the thing inside. So this quantity goes to infinity, and if this quantity goes to infinity, tangent inverse goes to what? Pi over 2. So this is minus pi over 2. Why is that? You know, the tangent inverse function is like this. This is the y, and this is the x coordinate. Xy coordinate. We have here minus, this is pi over 2, and this is minus pi over 2. This is pi over 2. And this is y equal to minus pi over 2. And we know that what? We have an increasing function for tangent inverse. This is y equal to tangent inverse of x. So if x goes to infinity, the quantity approach pi over 2. So the final answer is minus pi over 4. So what can you say now about the sequence of partial sum? It is convergent. And in that case, the series itself is convergent. Not only convergent, the sum is equal to minus pi over 4. So the series is convergent. Why it's convergent? Because the sequence of partial sum is convergent. It's convergent, sorry, this is convergent. And not only this, its sum is equal to minus pi over 4. Now, I give you an exercise to think about, because it's not always the first term and the last term only will survive. If you need to understand more about this, do the third part here. Test the series given here for convergence. N equal to 1 up to infinity. That is 2 over n plus 2. Okay? Do the same trick we did before. Try to use partial fraction, etc. But when you open the terms, try to figure out which terms will be cancelled out, which terms will not be cancelled out. Then discuss the limit as n goes to infinity and see if this is convergent or not convergent. It is convergent. The only thing I needed to observe, which terms will be cancelled out. Is it only the first and the last one? Or no, more terms will be survive at the end. Okay, fine. That is now what we did for geometric series, we did for telescoping series. Fine. Now we will study the importance of the nth term. You see, for any infinite series, we have an nth term, okay? And that term plays an important role of convergence. You see, if we have n equal to 1 up to infinity, and this is a n, what is the contribution of this term in the convergence? That will be discussed in our next point. Now let us see the contribution of the nth term in the convergence of a series. This is a very nice theorem that says if we have a series and we know that this series is convergent, then the limit of the nth term must be equal to 0. From where this came, actually, how to prove this theorem, just to give you an idea of the flavor of the proof of the theorem here. Okay, say this is the idea of the proof, if you like, to see this. Now let's go back to the definition. If we say this series is convergent, what does it mean convergent? It means if you take Sn, which is what? Sn is the summation of the first n elements, so that is A1 plus A2 plus A3 plus up to an. This is what we call Sn. Okay, fine. If it is convergent, it means the limit of Sn is a finite number. Since the series is convergent, okay, I will say here, before I go to discuss the convergence of the partial sum, what is Sn minus 1? The sum of the first n minus 1 elements. That is A1 plus A2 plus A3 plus up to an minus 1. Okay, if we look carefully here, again, I can add one more point. I will say this is an minus 1 plus an, because the previous term is an minus 1. Fine. Now, since the series is convergent, since it is convergent, it's given that it is convergent, what does it mean, convergent? It means the limit of Sn as n goes to infinity is a finite number equal to L. This is equal to L. But this is equal to what? As n goes to infinity, both of them will go to the same limit here, because n minus 1 goes to infinity and n goes to infinity. So it means also the limit of, this is as n goes to infinity, it's the same as the limit of Sn minus 1 as n goes to infinity. Fine. What you need to do is just to subtract these two things. If you subtract here Sn minus Sn minus 1, you will see that all terms will cancel out. All terms will cancel out except the last one. So in this case, we have Sn minus 1 actually is equal to an. And this is equal to what? Sn minus an minus 1. Now, if you push the limit as n goes to infinity, you have here the limit as n goes to infinity. And again here, this will be exactly equal to what? This will be, just to make space here, this is exactly equal to the limit as n goes to infinity of Sn minus Sn minus 1. And you know that these two are convergent, so, and both of them goes to the same limit, L and L, the difference will be equal to 0. So the limit of the nth term must be equal to 0 if the series is convergent. Okay, let us read it carefully here. Does it say that if the limit of an equal to 0, then the series is convergent? The answer is no. Be careful. If we have, in mathematics, if we have a statement A implies a statement B, it is not always that B implies A. Let me give you an example from your previous studies. That we said differentiability at a point implies continuity of the function at that point. So differentiability implies continuity. Does it mean that if the function is continuous, then it is differentiable? No. The absolute value function at 0 is continuous, but it's not differentiable. Same thing here, we say, if this is convergent, the series is convergent, then the limit of the nth term equal to 0. If the limit of the nth term equal to 0, it does not mean that the series is convergent. One famous example will be proved later for you, that the harmonic series, which is a series of the form 1 over n, that is the addition of 1 plus 1/2 plus 1/3 plus 1/4, this is a divergence series. Although the limit of 1 over n is going to 0, but it is still what? A divergence series. So we say in general, the converse of this may not be true. The converse may not be true. But we can get a very interesting statement here. The counter positive. In mathematics, always if you have A implies B, then not B implies not A. That can be gained always from this. This can be gained from this. Let me show you this. If you have differentiability implies continuity, we say not continuity implies non-differentiability. If we apply the same argument here we say if the series is convergent, the limit is equal to 0. What is the counter positive of this? If the limit is not equal to 0 or does not exist, so it is not equal to 0 at the end for any reason, does not exist, not equal to 0, what is the conclusion? The negation of this says if the limit is not equal to 0 or does not exist, the series is not convergent, meaning it is divergent. And this counter positive of this theorem is called divergence test. Divergence test. So what is divergence test? Divergence says look for an. If it does not go to 0 as n goes to infinity, the series for sure is divergent. I will write this as a summary and then apply it in some examples in the following part. Okay, let us see now how to apply the divergence test in a specific exercise. Assume we are given this series and he said, the question says, test the series for convergence. Is it convergent or not convergent? It is recommended always to take a look on the nth term and see what is the limit of it as n goes to infinity. Here we have an. An is the nth term expression, which is n squared over 5 n squared plus 4. Now, what is the limit of an as n goes to infinity? The limit of an as n goes to infinity is equal to, clearly we have 1 over 5. Why? You can divide by n squared, so this should be 5 plus 4 over n squared, and this is 1, so the answer is 1 over 5. Now, this is not equal to 0. Yeah, it is not equal to 0. Since the limit of an is not equal to 0 or does not exist, the series is divergent. So, the series is divergent by what we call divergence test. Divergent test. So this is the reason why it is divergent, because the limit of the an is not going to 0, and this is one application for divergence test, that always you check the nth term. If it doesn't go to 0, directly you say the series is divergent. We conclude this talk about series or infinite series for this specific part about the properties of infinite series. If we have two series, both are convergent, we have constant real number C, then we can also say that this new series, which is constant multiple of a convergent series, is convergent. The sum of two convergent series is convergent. The difference of two convergent series is convergent. Not only this, the sum of the constant multiple of a convergent series is the constant of the sum, constant times the sum. And the summation of the sum of two series is the sum of their values. So it is the sum of the first plus the second of the second, or the sum of the first minus the sum of the second. But here you need to be careful here. This is true only if both of them are convergent. Nothing said about if the series AN is divergent and the series is BN is divergent. If both of them are divergent, we should be careful here. If one of them is divergent, the other one is convergent, the sum and the difference is divergent for sure. Let me repeat this. If the series AN and the series of BN is are convergent, the sum of them, constant multiple of any one of them, is convergent for sure. If one of them is convergent, the other one is divergent, the sum, the difference is divergent. If both of them are divergent, we should be careful here. We should be careful here because you see, let me comment on this before I move to the last point. You may have two series that are divergent and the sum or the difference is convergent. Look for this. This series, which is at least we know until now 1 up to infinity, 1 over n, this is divergent series, okay? This is a divergent series. If you add it with another series of divergent type, let us say subtract it from another series, which is the same series actually, up to n, 1 over n. This is divergent, this is divergent. Okay, what about this series here? N equal to 1 up to infinity, 1 over n minus 1 over n. This is an, this is bn, and this is an minus bn. This is exactly what we have here. 1 over n minus 1 over n will be 0, and the summation of 0 is convergent. We can prove this by using the definition. Okay, although this series is divergent, this series is divergent, the difference of their nth term will give us a series which is convergent series. So we should be careful when we apply the properties here. The properties are hold true only if we have the two series are convergent. Then we can use the sum or the difference of the two series. Now let us see this nice question here. He said find the sum of the series. You can look carefully for the nth term. If we separated this as the first part and the second part, these are well-known series for us. So what we need to do now, we consider this. We need to investigate now what's happening if we just discuss the first one separately. N equal to 1 up to infinity. Let us start with the 3 over n plus 1. And the second one is summation of n equal to 1 up to infinity. This is 1 over 2 to the power n. We cannot say from the beginning that the sum of the series is equal to the sum of the two series. The sum of the two nth terms here, the sum of an plus bn. We cannot say it's always equal to the sum of the first plus the sum of the second. But if we figure out that this is convergent and this is convergent, then we will conclude that the sum of the series is the sum of their sums. So if we can find this is convergent and this is convergent, we can conclude that this one also is convergent by the theorem we have here. Not only this, the sum of the given series is the sum of the two sums of this series. So let us discuss now the convergence of each one separately. Now, let us see, for example, here n equal to 1 up to infinity. This is 3 over what? n plus 1. You know, we did this example. We did this example where it is what? Remember this. Recall that we discussed before this example that says n equal to 1 up to infinity, 1 over n plus 1. This is a telescoping series, and we found this is equal to 1 from our previous example. This is a telescoping series. So what can you say about this? 1 over n plus 1 convergence, so constant multiple, this is exactly equal to 3 times summation of n equal to 1 up to infinity of 1 over n plus 1, and that is a telescoping series whose sum is equal to 1. So according to the theorem, we have the sum of this is 3 times 1, that is equal to 3. We conclude this because the given series we have is convergent. This one is convergent. So for sure, this is convergent by the theorem we have. It's constant multiple of the series. That's one thing. The second point now. Now, let us investigate the second one. Consider this. Consider this series, which is n equal to 1 up to infinity. That's 1 over 2 to the power n. That's what we have. This is a geometric series. Clearly, it is geometric series. That is 1/2 plus 1/4 plus 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 plus. So in this case, this is a geometric series. With what we have here is absolute value of r is equal to 1/2. That is less than 1. So it is convergence. Not only convergent, we can find the exact sum of it. With the sum is equal to what? It is a over 1 minus r. That is equal to 1/2 divided by 1 minus 1/2, and that's exactly equal to 1. 1 minus 1/2 is 1/2. 1/2 divided by 1/2 is equal to 1. So what can you say about the series here? What can you say about the series here? Since both of these two series convergent, by the theorem we have, the original one is also convergent. I will conclude this discussion by writing the conclusion of this exercise that says, okay, now I will say since this series n equal to 1 up to infinity, that is 1 over n plus 1 is convergent. Telescoping series actually. And this summation n equal to 1 up to infinity 1 over 2 to the power n is also convergent. Then we have this. Then we have the summation of n equal to 1 up to infinity, constant multiple of the first one, added to the second one, is convergent. Not only convergent, and we have this. And we have this. The summation of this, n equal to 1 up to infinity, 3 over n plus 1, okay, plus 1 over 2 to the n is exactly equal to 3 times the sum of the first one, n equal to 1 up to infinity 1 over n plus 1, plus the sum of the second one, that is 1 over 2 to the n equal to 1 up to infinity, and this is equal to 3 times 1, that's 3 plus 1, which is equal to 4. Okay. Now, let us summarize what we did until now in series and see what will be our next point. Okay, fine. We define the meaning of series, first infinite series. Then we define the difference between series and sequences. The meaning of a convergent of series, we said it is simply just to find the nth partial sum and push n go to infinity and see if the limit of the partial sum sequence is convergent, then the series is convergent, otherwise the series is divergent. That's one thing. Then we introduce the meaning of geometric series, the meaning of telescoping series, and we discuss the importance of the nth term of the series, that we reach what we call the divergence test. That's if the limit of an, the nth term, is not equal to 0, the series is divergent. And finally, we can produce some convergent series from a given convergent series. So we can introduce any constant multiple here, and the sum and the difference of two convergent series are convergent. And by the way, that can be proved easily by using the definition. And this is just the properties of limits at the end. You have limit of Sn, limit of Bn, and then you can take the sum of both limit exist. You can always take the difference, you can take the constant out. That is basically what we have for infinite series. We will introduce more types of series in our next talks, and we will investigate the convergence of such series.